Is Jose Villén-Altamirano. Sorry. And he'll be talking about the restart simulation of non-Markovian queuing networks.
Very good. This work is a joint work with my brother Manuel and with Enrique Vázquez. First, we will make a brief description of the method and give some previous results. Then we will see the effective important function for non-Jackson networks, some simulation result, and conclusion. But in this method, set Ci and set nested set Ci are defined by means of a function phi taking values greater than or equal to certain threshold Ti. And in this figure, also the real set A is defined by means of this function. When the process enters the first set Ci, that is when it crosses up the threshold T1, the system state is saved at the point B1, and a number of simulation retrials are made, all of them starting with the system state, with the save state, and finish when they cross down the threshold. So only the last trial continue, and if it hits again this threshold, a new number of retrials are made. If one of the retrial of level 1 hits level 2, a new set of retrials of level 2 are made, and so on. In this case, the set A is including all set Ci, and the probability of the real set is calculated as the product of this conditional probability. And this is the unbiased estimator that is the same that with cruise simulation, except this term, Rm, that is the product of all the retrials from all the thresholds. In general, the set A has not to be defined by the important function. In this example, is a 2Q tandem network. We have derived this important function, that is a linear function of the Q length of the two nodes, but the real set is defined only for the 2Q, second Q. So these sets Ci are defined by the important function, but the real set is this one. In this case, the real set is not including all the sets Ci, and its probability is calculated applying the theorem of total probability, and the corresponding estimator is this one. In previous paper, we have derived the variance of the estimator and also the simulation cost, and comparing cost time the variance of restart and cruise simulation, we have obtained this formula for the gain or speed up of the method. We see in the denominator some factor that reflects inefficiency due to the first one, not optimal choice of the number of threshold or the distance between threshold. The second one, non-optimal choice of the number of retrials. Fo is represent the overhead of the algorithm, and this is the more crucial factor that will be analyzed later. We have derived this formula for the accumulated number of retrials, and with the rounding algorithm, it's easy to take a value close to 1. Also, we have proved that the threshold must be set as close as possible, so we must set as many thresholds as possible. It's robust against the choice of threshold. This factor is due to the overhead of the algorithm. We have an overhead per event because we have to evaluate the important function after each event compared with threshold values. And also we have an overhead per retrials because we have to save or restore the system state at each base V, and we have also to reschedule. This factor usually takes low values with exponential time, but with hyper-exponential Erlang time that will be used here is more time consuming, and this factor will take greater values. Well, to minimize this factor, we must, the main thing is to choose a good important function. But also, we must reschedule. It is convenient to reschedule at each BSUI when we start the retrials. And we must reschedule the scheduled arrival times and the scheduled end of service time. Otherwise, there will be high correlation between retrials. So it's essential to make rescheduling. In the case of exponential time, the rescheduling is straightforward due to the memory-less property of the distribution. And so we just obtain a random value of the whole service at this point, and it's rescheduling with exponential time. But with other distribution, we know that in this point, start the service, but we know that at this point, the service has not finished, so we must rescheduling, taking into account a condition that the service time will be greater than this amount. So the end of service time should be greater than BI. What we do is to obtain a random number for the whole service time at this point, and if the end of service time is lower than BI, we try again until it's greater than BI. Sometimes it takes many trials, and so we limit to only 50 attempts. Could be also 25, 30, 40, but a finite number. And if after 50 attempts, all the whole end of service time are lower than BI, we don't reschedule that time. We maintain the previous scheduled end of service. With this procedure, 98% or 99% of the time are rescheduled. The most important things to obtain a low value factor of FB is to choose an effective important function. We have derived in this paper formula for the important function for all type of Jackson networks. In the case of 3Q tandem network, these are the formulas. We see that is a linear combination of the Q length of the Q's and the coefficient are related with the load of the nodes. Depending of the load is one formula or other. In general, these are particular case of general Jackson networks. The real set is defined in a target node, taking values greater than or equal to L, and the important function is a linear function, linear combination of the Q length of the target node, of the Q length of the nodes directly connected with the target node at distant ones, and also for nodes at distant 2. All these coefficients are system parameters, are known, and as is not as clear as before, but also depend on the load of the nodes. So now we are interested in non-Jackson networks. We make these two questions. Will we fit for other networks the important function derived for Jackson networks? And the answer is, for some networks, yes, for other networks, no. Second question, will it be easy to modify that important function? And as we'll see now, the answer is yes. In general, the important function, as we have seen, is a linear combination of the Q length of the nodes, and the coefficients are function of the load of the nodes. In general, the lower the load of a node, the higher the value of the coefficient. For Jackson networks, we know that this probability is calculated as rho power n, and it's also this probability. But for non-Jackson network, it is not true. But this probability, we will use the value of rho obtained with this formula for non-Jackson network, and we will call it effective load, because this effective load is more related with this probability that we are interested in estimating than the actual load. So what we will do is to use just the same formulas as for Jackson networks, but instead of using the actual load, we will use the effective load obtained with the formula. For obtaining this value of rho, this probability can be evaluated with crude simulation for low values of n, and so it's easy to obtain rho. Yes. Well, rho is for each node. For each node, we obtain the load of each node in this way, and then we put in the formula this effective load. In case of Markovian networks, the actual load is the effective load, but for non-Markovian networks, it's different. So we see some simulation results. First, we describe the topologies that we have simulated. We try to look for difficult topologies. The first one is a two-node network with a strong feedback. A customer leaving a node, join with probability 0.8 to the other node, and with probability 0.2 leave the network. The real set is defined in the second node, and to make it more difficult, the bottleneck is in the first queue, the first node, and the load is double the other load. The second topology is a 3-queue tandem network. The second example, with this load, the difficulty is similar to the 2-queue tandem network used in many examples, in many papers. But the first case is much more difficult because the bottleneck is the first queue, and then the second queue is bottleneck with respect to the third queue. And the easiest case is the third one. Next topology is a network with 7 nodes. Customer can arrive from the outside to any of the nodes. The nodes 5 and 6 are directly connected with the target node, and node 1 to 4 are at distance 2. And so we have chosen also 3 sets of loads. In the first one, the more load networks are the networks at distance 2, is the more difficult case. Then the load at distance 1, and then the target. In the second network, in the second set, the more load network at distance 1, and the easiest case is when the more load network is the target network. And finally, the last topology is a large network with 15 nodes. 4 of the nodes are at distance 3, so as we commented before, they are not included in the important function. A customer leaving a node can go to other 8 nodes with probability 0.1, and also the load of the target node is one of the smaller load to make it a little bit more difficult. For these 4 topologies, 8 cases, we have proved with this combination of inter-arrival and service time are 6 combinations, so we have simulated 48 models. The Erlang distribution have a shape parameter 3, so the coefficient of variation is 0.58, and we have chosen an hyper-exponential distribution with a high coefficient of variation. 0.42, in both cases, far from the exponential case that, as you know, is 1. Let's the result for the first example. Well, in all the cases, we have obtained probability of the order of 10 power minus 15. We change the value of L, and we finish the simulation when the relative error of the confidence interval is smaller than 0.1. We will show in detail only the case, Markovian case, and the more difficult case could be hyper-exponential interarrival time and Erlang service time. Here the actual load is 0.33 in the two cases, but the effective load for the second case is 0.22 for the target node. For the other node, this is the actual load for both cases, and this is the effective load for hyper-Erlang case. In both cases, in 2 minutes, around 2 minutes of computer simulation, we could estimate this probability with a relative error of 0.1. And we can observe that the factor related with the important function is the same in both cases. This is the gain in time. It means, well, with good simulation, it will take 10 power 10 times more to obtain this probability. And we observe also that the factor related with the overhead is doubled for the hyper-Erlang case due to the problem of rescheduling. We have studied also the robustness, and as a stable result, we mean as a stable result, computer time less than double of the optimal were obtained for coefficient between 0 and 0.21. For the 3Q tandem network, the load of the target node, this effective load in the third case. We see the coefficient for the Markovian case are quite different for the coefficient obtained with the effective load. And here the computer time is the more difficult case is the first one, 3.3 minutes with the exponential case, and 16.6 is the worst case of the 48 cases simulated. It is the greater computer time for estimating probability of the order of 10 power minus 15. We see here that a high value of FB, it means that it could be improved, that important function. And the other case, we obtain better result. For the network with 7 nodes, we obtain much better result, less than 2 minutes in all the cases. Factor FB very close to 1. It means that this function is very effective, very good function, important function, close to the factor close to 1. And here we can observe that the coefficient of the hyper-Erlang are more close to the coefficient of the Markovian case. So as it is also more robust for these cases, for the easiest cases is more robust always, the value of the coefficient can change more. We obtain similar result for the hyper-Erlang case with the coefficient derived for Jackson network. So for this case, we could have simulated with the same coefficient obtained for Markovian network. The same occurs with the last example. These are the coefficients of the Markovian case, and these are the coefficients obtained with the effective load. These are a little bit greater. As we mentioned before, the 4 first nodes are not included in the important functions, so their coefficient is 0. And in 3 minutes for the exponential case and 16 minutes for the hyper-Erlang case, we obtain this probability with this relative error. The factor FB is also close to 1. And as before, similar results are obtained for the hyper-Erlang case with the set of coefficients coefficient derived for Jackson network. For the other four combination of interarrival and service time, interarrival exponential, service time Erlang, hyperexponential exponential, Erlang exponential, and Erlang, analogous results have been obtained. In general, better than the hyper-Erlang case, but worse, of course, than in the exponential case. For these cases, for simulating the network of 7 and 15 nodes, we use the important function derived for Jackson network without using effective load. But for the 3Q tandem network and for the 2-node network, we use the effective load, calculate with this formula. So we make this calculation previously using crude simulation for a low value of n, and usually 4 or 5. And so, as conclusion, formulas of the important function derived for Jackson network lead to very good result in non-Jackson networks, just changing the actual load of the node by the effective load. Calculate, as we have mentioned before. Probability of the order of 10 power minus 15 have been estimated with a relative error of the confidence interval lower than 0.1 within short or moderate computation time, 16 minutes the greater computational time, in 48 types of networks, as we have seen, with different topologies, different loads, and different interarrival and service time. The networks have been chosen because they are usually classified as difficult networks in the real event literature. The worst results are obtained when the dependence of the target queue on the queue length of the other queues is very high, as it occurs in the 3Q tandem networks, and also when the bottleneck is in the other queues. As a consequence, the efficiency of restart often improves with the complexity of the system. We have seen that we obtain better results with the network with 7 nodes and 15 nodes than with the 3Q tandem network. And finally, this type of formulas could be applied to many other non-Jackson networks for estimating real event probabilities. Thank you.
Are there any questions? Okay, so let's thank the speaker again.